Hello, this is Algebra 1, Chapter 2, Section 6, Ratios and Proportions. And so, before we get started, I just want to give you a couple of definitions of what a ratio is and what a proportion is. A ratio is a comparison of two numbers by division, and we can represent ratios in a couple of different ways. X to Y is one way. They use a semicolon. Is that a colon or a semicolon?
It's colon.
I think it's a colon. It's not a semicolon, it's a colon. X to Y, it means the same thing. And of course, division X over Y. Those are all ways that you can make a comparison of things. And of course, you've seen ratios in everyday life. My favorite, I don't know if my favorite, but it's one that comes up a lot, is you hear a lot of commercials where they talk about toothpaste, for example. They'll say things like, 1 out of 5 dentists agree that blah, 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 blah. Those kinds of things are ratios. And so, anywho, those are your representations. And then we have a proportion. And a proportion is basically when you take two ratios and make them equal to each other. So a proportion is an equation that states that two ratios are equal. And so we are going to do some examples with some ratios here. And our first example says, determine whether 2/3 or 2 to 3 and 16 to 24 are equivalent ratios. You will have equivalent ratios if they simplify to the same thing. This is the question right now. Now obviously between 2 and 3, those are both prime numbers. They can't really simplify to anything. So that's the left-hand side ratio is already simplified. But we know that if we take 16 and divide it by 8, that we will in fact get 2. And if you take 24 and divide it by 8, you will in fact get 3. And so then when you simplify 16 over 24, you do get 2 over 3, which is the same thing as this 2 over 3. So in this case, the answer is yes. And because it simplifies to 2/3. So there we go. These are in fact equivalent ratios. I've justified my answer by simplifying it to 2/3. And so now you can try a couple on your own. I have 6/10, 2/5, and then over here on part B we have 1/6 and 5 over 30. And you can determine whether or not they're equivalent ratios. And then meanwhile, we're going to go on to the means, extremes, property of proportion. That is a real long name. It's also known as, aka, cross products. So you've probably heard of this before. When you write a ratio in the other way, which is to say A to B or C to D, if you write it that way, then basically what you're seeing is that in here, the B and the C, what's on the inside is what we call the means, the inside, and then these A and D are called the extremes. And so basically when you see it this direction, you have this little cross product thing, and it basically means that if you have two ratios equal to each other, that the product of the extremes is equal to the product of the means. So A times D would be the extremes, and then B times C would be the means, and that product, they would be equal. So here we have A and D, which are, again, what we would consider the extremes. And then we have the B times C, which is what we would consider, this is like my extremes. And these are my means, because the means are on the inside, and the outside ones are the extremes. Now it's not entirely that important that you memorize what extremes and means are, but it is important that you understand how the cross product works. So, anywho, and of course B and D can't equal 0, because if they did, we would have division by 0, that would be a problem. So here we go. Example 2 says, use cross products to determine whether each pair of ratios forms a proportion. So again, the question here is 2 over 3.5 a proportion? This would be a proportion of if the cross products were equivalent. So what I'm asking here is 2 times 14 the same thing as 8 times 3.5? That is the question, folks. And so 2 times 14 is 28. And 8 times 3.5 is also 28. And so because those are equivalent, then these two ratios do in fact form a proportion. So the answer for part A is yes. They do form a proportion. All right, so now we want to try part B. Same idea. The question becomes whether or not, if I set this up 0.3 over 1.5 equivalent to 0.5 over 2.0, and if I do a cross product, is 0.3 times 2.0 equivalent to 1.5 times 0.5? That is the question. So 0.3 times 2.0 is 0.6. And 1.5 times 0.5 is 0.75. And as we can see, they are not equivalent. So in this case, these two ratios do not form a proportion. All right, so that's how you determine whether the ratios form a proportion, is set up the cross products, and if they equal each other like they did in part A, then the answer is yes. If they do not equal each other like in part B, then the answer would be no. So now you can try a couple on your own, and we will move on to solving a proportion. So in this case, we do not have numbers for all of the 4 components, the A, B, C, and D. But we are here to solve what x value would make this proportion true. And so we do it with the cross product, and we say 5 times x is equivalent to 10 times 3, which in this case is 30, and then you just solve for the variable. So we divide by 5, and it turns out that if x is equal to 6, then this will be a true proportion. So that's how we solve. It says if necessary, round to the nearest hundredth. In this case, it's not necessary because 6 is an integer. Part B gets a little trickier, not so much in the fact that you still have to do a cross product, but you'll notice that on the top of the fraction here in part B, we have x minus 2, not just x. And so the reason why that gets complicated is because people will oftentimes forget to distribute. So I just want to remind you not to do that. We take x minus 2 and times that by 7, which is the extremes here. And then we have 14 times 2, which is 28. Okay, so it's very important that you distribute the 7 times x, which is 7x, and the 7 times negative 2, which is negative 14, equal to 28, and solve for x. So we add 14, 7x equals 8, 9, 10, 11, 12, so 42. Divide by 7, and lo and behold, we get that x equals 6 yet again. That was interesting. 2 different proportions that both have the same answer, which is 6. All right, don't expect that to happen all the time because it won't, I assure you. But now you can try these on your own. And then we will go to some of the applications that you can do with ratios and proportions. And here's one of them, is unit rates. So a rate is a ratio of 2 measurements having different units of measure. So for example, the most common rate is usually speed. You're driving, you're going 5 miles per 1 hour. That would be 5 miles over 1 hour. So you have a fraction, 5 over 1. However, the units are not the same. It's not miles to miles, it's miles to hours. So it has different units of measure. That's a rate. A unit rate is a rate that tells how many of one item is being compared to one of another item. In other words, this is a unit rate because it's to 1 hour. But I could also say 25 miles per 3 hours, or even 4 hours, or 5 hours. Let's make it easy, and let's do 5 hours. This is not considered a unit rate. It's a rate, but it's not a unit rate because it's comparing it to 5 hours. But we could take the 25 miles to 5 hours, and it would be the same thing as, this would be the unit rate of the same idea. If you reduce this fraction, 5 goes into 25 5 times, 5 goes into 5 once, this would be the unit rate, this would just be a regular rate. So a unit rate is when you compare it to one of the item. So how do we apply that to a problem? Here we go. Example 4. In the past 2 years, okay, so 2 years, a retailer has opened 232 stores. So their rate for opening stores is 232 stores per 2 years. This is not a unit rate because it's comparing it to 2 years, not 1 year. Okay, just as information for you. If the rate of growth remains constant, how many stores will the retailer open in the next 3 years? So you can actually solve this a couple of ways. You can convert this to a unit rate, which would be to simplify the expression. So we know that 2 goes into 2 once, and 2 goes into 232, probably 100 and, where's my calculator when you need it? Okay, so 232 divided by 2 is 116. All right, so 116 stores per 1 year. Now this is what we would call a unit rate. And then because they want to know for 3 years, you would times that by the 3 years. Okay, the years would cancel. And 116 times 3 would give you a whopping 348 stores. That is using a unit rate to solve the problem. But you can actually also use a proportion. You could say 232 stores on top and the years on the bottom. Then you can equate that to, we don't know how many stores, x over the 3 years. And then you could do it this way and get 2x equals 3 times 232, which is 696. And then divide the 696 by 2, and you would still get the same answer, which is, of course, 348 stores. So you can use a unit rate, or you can use a proportion to solve this problem. So now you can try this little guy right here. And then we have our last example. And our last example is dealing with scales and maps and that kind of thing. So basically what's happening here is, I don't think very many people read maps anymore because now we have Google Maps. And Siri will just tell us where to go. But back in the day, we used maps for everything, or you can even think of them as scale drawings, models. Sometimes people make a smaller replica of a building, for example, when they want to show what a building will look like once it's built. So they have, obviously scale drawings of that because obviously they're not going to build a full-blown replica of what they're building. That would be pointless, okay? So you make a small version of it, and so if you want the scale to be right, you have to use a proportion. So here we go. The Ramsey Cascades Trail is about 1 1/8 inches long on a map. So we have map versus actual. Because clearly on a map it's going to be smaller than it is in actuality, in reality. So you can make that into a proportion. On a map, the trail is 1 1/8 inches, which is basically the same thing as 9/8 of an inch. That's on the map, okay? And on the map, we know that 3 inches is equivalent to 10 miles. So on a map, 3 inches is equivalent to 10 miles. So what I've done here is on the top of my fractions, I've placed the map measurements. And on the bottom of the fractions, I've placed the actual measurements. Okay, so it doesn't really matter which one goes on top and which one goes on bottom. You could do actual over map or map over actual. But what does matter is that you're consistent. So once I've decided that map goes on top with the 3 inches on the map, 10 miles in actuality, then on the other side, the 9/8 inches, which is on the map, has to coincide with X on the bottom for actual. It's asking us what is the actual length of the trail. So again, over here, this is the map measurement, and I'm looking for the actual. I don't know what that is, so when I don't know what it is, I call it X. And now I have a proportion, and I can solve it very easily. 3 times X, let me get over here, 3 times X, and then 10 times 9/8. And so 3x is going to equal 10 times 9/8, which is 11.25. And then divide by 3. And it turns out that I get 3.75, or also known as 15/4 miles. So what is the actual length of the trail? The actual length of the trail is 3.75 miles or 15/4 miles. Alrighty, so that's how you can use a scale to set up a proportion and then solve a missing length. Alright, so you can try this last do-it-yourself example, and once you've done that, you will have completed your notes for today, and I will see you in class. Thank you for watching.